It's a pleasure being invited here to give this talk on impedance planimetry, a technology I've been working on and off for about 25 years by now. And no future without giving some history too, so I will briefly go through what is impedance planimetry. I will go into more details about 3 applications of impedance planimetry and use that to discuss what will we see in the future. And first, a few disclosures. These are actually the 3 technologies I will discuss during this session. All of them have been technology transferred already. One, EndoFlip, as you may know, is commercialized by Crossbond, an Irish company, and I have a minority shareholdership in that company. So impedance planimetry, it's a balloon, or I prefer the word bag extension technology, where it's, let me see, where's the pointer? Where we, using Ohm's law, measure the cross-sectional area in the middle of the balloon by using a simple electrical principle. And it's important to emphasize that it's actually the cross-sectional area we measure, it's not the diameter. Of course, you can derive the diameter if it's a circular cross-section. And this is, it was basically a system we built up in my group about 25 years ago. So we built the hardware, the software, the probes, everything by ourselves at that time. And it was used quite a lot as an independent technology by our group and with collaborators in the 90s, late 80s and 90s. And here are some examples from some of our clinical trials, the clinical studies. An example here from a study in patients with severe systemic sclerosis. The upper tracing here is from a normal subject, so we would do a balloon distension here. This would be the cross-sectional area during a series of different distensions with preset pressures. This would be the proximal pressure, the balloon pressure, and the distal pressure. And as you can see, there's quite a lot of secondary peristalsis being evoked by the balloon distension. And if you compare that to the patient with systemic sclerosis, you see a completely different pattern. The cross-sectional areas at the same pressure levels are much higher, so it's dilated. You see almost no evoked motility here, and we could also do some analysis that clearly showed that the wall was stiffer, which would also be expected, of course, in this type of patients. Probably the most significant clinical study we did was a study we did with Rao from United States on patients with non-cardiac chest pain, or we don't call it that any longer, or functional chest pain, where we showed that distension could be used to subtype patients into hypersensitive or hyperreactive subtypes. And that, again, led to other studies. This is from a study done in our laboratory when I worked in Aalborg in Denmark, where we did repeated distensions in a group of normal volunteers. That's an example here. This is, again, the cross-sectional area, so we would do 10 distensions to the same level. This is the pressure inside the bag, and this is the sensory level. And if you compare that, or a normal person can easily take 10 distensions up to the pain threshold, which would be 50 on this scale here. If we did the same in a patient with non-cardiac chest pain, you can see a quite different pattern. Already after 4 distensions, the patients ask us to stop. The pressures look quite different, but if you look especially at the VAS curve here, you can see that it increases from the first time up to the 4th time where they tell us to stop. So clearly this is a test that can be used to differentiate these patients. At that time, we were also heavily influenced by muscle physiology. And you may be familiar with the striated muscle links tension diagram. So basically, if you have a muscle, you stretch it, there will be a certain optimum point where it can generate the most force. If it's stretched less, if it's stretched longer, then it can generate less force. That's why we have this curve shape here. Also, there will be a relation for the velocity force. Basically, the less force the muscle has to work against, the faster it can contract. And that can be converted into a power curve where there again is a local maximum. And finally, from heart physiology, we know the pressure volume curve from the left ventricle, the well-known loop here when it goes through diastole and systole. And we were kind of thinking, okay, if this can be done in heart muscle, in striated muscle, wouldn't we be able to see the same kind of patterns in GI muscle? And these examples show exactly that that's the case. Here's a length tension diagram. This is from the human esophagus, showing both for phasic and tonic contraction that there is a maximum force velocity relationship where we closely analyze the velocity of the contractions on the CSA curves. Exactly the same curve shape as we saw before. And finally, like the cardiac pressure volume loop, we could reproduce that here with different volumes inside the bag. Here it would be 10 milliliter, 20 milliliter, 40 milliliter. This is data from the human small intestine. So exactly the same features exist for GI muscle. And the reason I show this is that I think many have forgotten this kind of studies and this kind of more detailed muscle analysis that we can derive. Anyway, impedance planimetry turned out to be the base technology in the three applications I want to talk about today. One is called a multimodal probe. The work was mainly driven by Asbjørn Dreves from Denmark. The functional luminal imaging probe, or FLIP, where the work was driven by Barrick McMahon. At least for this time period, others have taken over after it commercialized in 2009 or 2010. And there was actually also some early preliminary work where we played around with multiple electrode sets back from 2003. And then the last device I will go into detail on is the Fecobionics device, and if you're more interested in that, there is a poster today. So for the multimodal probe, it uses impedance planimetry, so there is a bag here that can be distended, that is a mechanical distension of the tissue of the human esophagus, for example. But in the multimodal probe, we combine it with other stimulation modalities, such as we could make an acid injection here. That would be a chemical stimulation. We could change the temperature of the fluid inside the balloon, so we could also make a thermal stimulation, or place electrodes on the surface of the balloon or on the catheter, and that would be an electrical stimulation. So it would be combine these four different types of stimuli. And the idea behind it was really to challenge the whole gut-brain system. We wanted to control the stimulus, so we want to know exactly how much do we stimulate it mechanically, thermally, and so on. And then look or evaluate the local reflexes. So how would the organ, the intestine, the esophagus contract? What would be the signal sent to the central nervous system? We could measure referred pain areas or do measurements on brain responses. And just one example, we have published quite a lot on this technology, so you can quite easily find the papers out there. This is data, again, from a patient with functional chest pain. In this case, we would do 2 distensions in the esophagus with an interval between them. This is the cross-sectional area, this is the pressure, this is the VAS level. So we went up to moderate pain that would correspond to 70 on this scale. And you can see that the first distension and the second distension, they look pretty much alike. But then if we injected acid into the esophagus, or perfused the esophagus with acid for about 10 minutes or so, then and repeated the distension test, then we would see a completely different pattern. I mean, these would be lower than these ones, but especially if you look at the sensory level, after doing the first distension, we never get back to baseline level, and it's protracted here. And after doing the second one, it seems even worse. So clearly this patient is hypersensitive to acid. And this is revealed by combining these 2 tests. This is the only example, but we also would combine this with the thermal testing, with electrical stimulation, to look at interaction between these different modalities. And that makes a lot of sense since we have different types of receptors in the esophagus wall, in the intestinal wall. Some are mechanosensitive, some are thermosensitive, some are more polymodal. And well, we're not going through this scheme, but I think we studied about 500 or 600 patients in total with a primary interest on the functional chest pain, on NERD and GERD, where we had indicators for if it was one disease or another disease. Then to the second technology, FLIP or EndoFLIP. The basic difference here from impedance planimetry is just that we place more electrodes here. So instead of measuring one cross-sectional area, now we could measure basically as many as we want. The commercial version has 16 measurements in a balloon that's about 12 centimeters long. In the beginning, and this is all the work done by Barrick McMahon, we would use a system just with 8 cross-sectional area measurements. And we would get this type of curve, like 8 tracings, and nobody would know how to interpret 8 tracings like that. But we would express it as a geometric plot instead of, and the main interest was in the lower esophageal sphincter, or the esophagogastric junction, where we would typically see this hourglass shape in the healthy volunteers, in different types of patients. And we also would develop some kind of color contour plotting. This was actually done already back in 2009. And it soon found quite a lot of applications. As I mentioned before, I think it was commercialized in 2009 or 2010, been adopted by several groups. This is an example where from an achalasia patient, where we see a very tight sphincter here. So the balloon primarily fills up in the esophagus, down in the stomach. After doing a hilar myotomy, the geometric pattern changes completely, indicating that the muscle has been cut, so the muscle tension is released. And I think the last one is after fundoplication, so where they try to reconstruct the ETJ. So this is just one example of use of the technology, where it actually can guide the surgeon to how much muscle that should actually be cut. One new thing that came about is the FLIP topography, so just like high-resolution manometry, where we would have the pressures at the different positions on the y-axis as a function of time. In the FLIP topography plot, we would simply have the cross-sectional areas here, and the color would indicate how distended it is in different areas. This is from a healthy subject, looks quite busy, a lot of contractions here. This is from a patient with achalasia. And they're quite useful, these plots nowadays. So what other flip applications are there? There's quite a lot. I know there's a lot of work ongoing. I think one of the more important is the use as a sizing tool. POEM has in many ways replaced Heller's myotomy. I know there are studies going on, and there has been published studies where flip is used during POEM procedures, during gastric operations. There's definitely application, and there has been papers on non-obstructive dysphagia, EOE, 7-8 papers at least on anal physiology, primarily on normal subjects and on patients with fecal incontinence. And then, as I showed you before, I think in the future it will find a lot of space or use as a motility assessment tool. Papers are starting coming out where the motility is analyzed in much more detail. The last of the three applications are called Fecobionics. So Feco means it has something to do with defecation. Bionics means electronics in biology. We will get back to that. So basically, we were interested in developing a device that could give us the same data as we would get from Fecobionics, from the balloon expulsion test, and from high-resolution manometry, and try to integrate that into one device. And you're probably familiar with the balloon expulsion, Fecobionics, and high-resolution manometry. So we wanted to kind of rethink that. And if we wanted to do that in one test, that meant that we would have to measure both the anorectal angle here and how it changed during defecation. We would need to know the shape of the device when it's being expelled, and we would need to get some kind of pressure profile. So basically, we would insert the device into the rectum or as high as we could get it, inflate the bag, and then to the urge to defecate level, and then ask the patient to defecate it. These are some of the early prototypes, bendable core with all the electronics inside. This is how it looks today. It's still wired, but we have a wireless version coming out very soon. So this would be inside the rectum, be expelled, send data in real time to a receiver outside, and we can look at the data, how it bends, what the pressure profiles are on an iPad right next to it. And as I mentioned, we could obtain the shape of it during expulsion, a pressure profile, and also get data for the anorectal angle. So let me go quickly through those three. So this is geometric data obtained by impedance planimetry. So we had electrodes for impedance planimetry on the core of the device inside the bag. And here you see it located in the rectum. Here it's being expelled, so this is outside. And all this tissue geometry here is actually computed from the impedance measurement, because we measure the luminal dimensions. And when it passes on the way out, we obtain all the data and we reconstruct the geometry of the organ afterwards. These are, of course, only two still pictures. Here it's in the rectum, here it's just being expelled. But that can also be shown as a video that is, I think it's in slow motion, so slowed down about 10 times, where you would be able to see the expulsion. So here it's located in the rectum. Now it starts to move. You can kind of see how it slides through the internal anal sphincter, reshapes afterwards, and finally is expelled completely. And here we have the balloon pressure pattern. So that's kind of quite impressive that we can reconstruct the geometry of the region. But what was even more promising was not the impedance data. In this device, we would measure the pressure in the rear end and in the front end. So it was not side pressures as you would see normally in high-resolution manometry or in other manometry devices. And here we have a display during an expulsion with a front pressure, that's the blue line here, the rear pressure is the green line. And the red one is the difference between these two pressures. So the rear pressure faces up in the rectum towards the abdomen. The front pressure faces the anal sphincters. So the expulsion starts here. You can see the two pressure curves, they follow each other tightly, so they measure basically the same increased intra-abdominal pressure, but at some point here they start to deviate. This pressure, which is down against the anal canal, probably measures anal canal relaxation or internal anal sphincter relaxation. At some point it reaches a top, a maximum, where it starts to pass through the anal canal, and here it's out in atmospheric pressure. So that's the front end of the device. The rear end of the device still feels the abdominal pressure that continue to increase while the subject tries to expel the device. At some point that reaches a maximum, and this part would start to move into the anal canal too. So if we look at the difference between these two, you can see the different slopes here. That means we can actually divide an expulsion into 5 different phases, just based on these two pressure measurements in the front end and the rear end. This healthy subject here actually had some problems expelling the device completely, so he was still sitting in the anal canal, and he had to make like 3 contractions before it was fully out. This is not what we see normally. Normally phase 5 would be quite a lot shorter. But it shows some of the potential with this kind of pressure measurement. And finally, about it, we have 2 gyroscopes in the device, one in each end, and we can use that to measure the angle in the device. And as the device slides from the rectum into the anal canal, it has to change orientation. And that is also nicely measured by these 2 gyroscopes here, so they change direction, and here it's out of the body. And if we again subtract these 2 from each other, we get a measure here of the anorectal angle while it passes. So the talk was about the future of impedance planimetry. I think what you have seen will to some degree be the future. But we need to discuss this in terms of design, analysis, and applications. And I think for the design, in the future, we will see a lot of diversification. Of course, we need standardized standard catheters for our clinical trials and so on. But I think there will be a need for custom designed catheters. That's the only way we can innovate. That's by making variations of devices. And that will be driven to a large degree by research hypotheses and possible applications. I also think that there will be a need for higher spatial resolution, even though in the endoflip now there's a very good resolution with 16 measurements. For some applications, we would need an even higher resolution. Just like with high resolution manometry, see how much we gain from going from 5-6 pressure measurements up to 20 or 24 or even more. I also think that there will be more integration of technology. We have already integrated high-resolution manometry into our multimodal probe. So in addition to stimulating with these 3 or 4 modalities, we will also get a high-resolution pressure profile. It can quite easily be combined with mucosal impedance measurements. And this is one of our new prototypes that is being produced right now. I also think there might be some integration between the multimodal and endoflip. I can certainly see how acid injection or sensitizing the tissue could be very useful in future flip studies. So that was the design. For the analysis, I think we need a lot more comparative studies on parameters. Many groups now use compliance measures, distensibility index. It's fine if you can show a difference, but if you cannot show a difference between two groups, that may easily be explained by variation, and other parameters may be more optimal for showing those differences. The color contour plot, I already mentioned it. It will be very useful, but I think we would need to see more advanced analysis, automated analysis of the color contour plots. They're quite easy to interpret for the human eye, but computerized analysis will definitely be helpful in the future too. And we would need more advanced mechanical analysis. I mean, these tools are mechanical tools, basically. The GI tract has a mechanical function. So we need to move from the more simple measures to more advanced analysis and computer modeling. And finally, the applications. The reason I showed you the muscle physiology data in the beginning is that I hope it will get a revival. I think there's a lot to gain from really considering how does the muscle contract. It gives us a lot of information, especially if we can control the stimulations as we can with the multimodal device. I think we need to see more studies again on functional GI diseases. For applications, I would definitely see an application for FLIP in sphincter of Oddi. I think there's been 1 or 2 published studies published, but there's definitely room for more, but it would require custom designed probes again. FLIP has already moved into the anal canal, the pyloric sphincter. You would find studies there, so sphincter of Oddi could be a future application where it could be useful. Fecobionics, we're already planning colonic studies, so we're not just staying in the anal rectum. We have kind of well-described hypothesis already for the whole colon for this device. But it must be driven by clinical needs and research hypotheses. It might sound like that it's more technology-driven, but it has to be driven by the hypothesis we can generate as scientists. So the concluding slide, there are currently these 3 applications I've been showing you. FLIP is commercialized. There are new applications for FLIP, new analysis possibilities. The 2 others, Fecobionics and the multimodal, the wider use depends on commercialization. Right now, it's a research tool used by several groups, but if it really needs to go out there, it needs to be commercialized, so it can be implemented in lab work around the world. I already mentioned there are new technology on the way, combination of technologies. Analysis needs to be considered very carefully. We need to do some optimization on parameters before we reach conclusions. And then I think we will see a lot more of what we call bionics, and that's why I call one of the devices for Fecobionics. So electronics in biology or biomechatronics. And when you think about these words, you think about like these Terminator things that are half man, half machine, cyborgs and so on. But it's coming. It's coming into our life. Probably 15, 20 years later, all of us will have a robot like that in our home, pleasing us in any way we may want. There's several groups working on intestinal robots that can crawl around in the colon, probably also in the small intestine, do measurements, send data out. So I think this is really where we will see a lot of development, and I would be happy if we would see impedance planimetry and pressure profiling built into that kind of systems. Thanks a lot for your attention.